This diagram you've seen before. It was in a previous lesson, I think in week 1, where we talked about just the terms really and the relative amount of energy. And so if you want to change something from the solid to the liquid phase, of course we call that melting. There's another fancy chemistry sciencey word for it. It's called fusion. But nonetheless, if we can call it melting. There's nothing wrong with that. But one of the differences between solid and liquid is the amount of energy. Liquid molecules have more kinetic energy than solid molecules of the same type. So that would be an endothermic process. If I melt something, that means I put energy into the system being the substance that we're melting, right? So if I melt something, I'm putting energy into the system, and so that's an endothermic process. And so you can see how that is the case in all of these where we have the up arrow, right? Sublimation, melting, vaporization. But then if we go in the opposite direction, if we cool things down, for example, we take a gas and we condense it back into a liquid, so condensation, in order for those gas molecules to become liquid molecules, they have to release energy into the surroundings. So the energy in the form of heat goes from the gas molecules into the surroundings. Therefore, those molecules can become liquid molecules. So they are exothermic processes. So now let's talk about this new term called enthalpy. It's symbolized with a capital H. I don't know why, but enthalpy, it's a lot like energy. So I'm going to give you the paraphrase definition, then we'll talk more specifically about what it is, technically speaking. So paraphrase definition is this. It's the total energy of a system plus the amount of energy required to make room for it. So the analogy that I often use is if a person writes a book, right? A lot of energy went into writing that book. So think of the book as the system. So a lot of energy went into writing that book. But that's not necessarily the end of the story, because if that person's going to put the book on a bookshelf, they kind of have to scoot the other books out of the way. They have to make room for that new book. So that's enthalpy. Enthalpy is that energy that's required to create the system, that total energy of the system. But it also includes that energy required to make room for that system that you just made. Okay, so just a more chemistry example is in this animation, you can see that somebody dumped baking soda into vinegar. So you have vinegar, you put baking soda in a balloon, okay? You dump the baking soda into the vinegar and it creates a gas. Okay, so the enthalpy change would not only be the energy change when it goes from vinegar and baking soda to the gaseous products, but it also takes into account the energy that's required to make room for those gaseous products, because that requires some energy to make room for all those gaseous products. It expands that balloon. It does some work, right? Work expands some energy is expended in expanding that balloon. So that's what enthalpy is. It's just the energy of the system that you're creating or that's been created, or just the change in energy. Really, it could be a negative amount, it could be a positive amount, but it also takes into account the amount of energy that's needed or is there to make room for the system. And again, that can be a positive amount or a negative amount. Now, in chemistry, the only time where that part of the energy required to make room, the only time that's important is when you have a gas. Okay, and so we typically won't deal with that situation, but you should know about that. Okay, so hopefully you understand better about what I mean by enthalpy, because that's the term that we're going to start using now. Okay, we're going to say less and less energy. We're going to say more and more enthalpy. Okay, because enthalpy includes the energy, but it also includes a little bit some of the more important details, and it's just more technically accurate. Okay, but here's the good news. So a change in enthalpy is also going to be the same as just the total energy change when you carry the reaction out at constant pressure. Okay, so just by definition, it is the energy change for a reaction or process if it's carried out at a constant pressure. Okay, well, we've already learned about that, okay, yesterday when we talked about heat. Heat was symbolized with the letter Q.
Okay.
So basically, enthalpy is the same as Q. It's the same as the heat flow if the system is at a constant pressure. Now, again, at the general chemistry level, that's most of the time, because here's one example of being at constant pressure. If it's open to the atmosphere. So any reaction that I would do in a beaker or an Erlenmeyer flask, it's experiencing a relatively constant pressure. The pressure in the atmosphere doesn't change all that much from day to day, from hour to hour, from minute to minute. So it's essentially at a constant pressure. And so anything that we can measure as heat flow, Q, and we talked about how to do that yesterday with calorimetry, a coffee cup calorimeter. So any of those numbers we can also use to describe the change in enthalpy. So another important idea or concept behind an enthalpy change, a delta H, is that it's pretty much the same as the heat flow, because most of the reactions that we observe or most of the processes that we're concerned about happen at a constant pressure. Why? Because we do things on Earth that are open to the atmosphere. Now there are certain types of experiments that you can do that are not open to the atmosphere, but we don't get into those in this course. Okay. Now, the sign conventions are the same as what they were for Q. So the things that we learned about heat flow, Q, yesterday, we can say about delta H today. So if Q was positive, that was endothermic. So I'm also going to say if delta H is positive, greater than 0, it's endothermic. If Q was negative, that's exothermic. So the same thing for delta H. Delta H, if it's negative, then that is an exothermic process or reaction. All right, so you can go back to that phase change diagram now and talk about how the delta H of, for example, condensation, that would be a negative value because that is an exothermic process. When something condenses from a gas into a liquid, it releases energy into the surroundings. The system loses energy. So that means it's going to be a negative change in enthalpy, less than 0, and therefore it's an exothermic process. Okay, so the other thing that we're going to do with this delta H is we're going to put subscripts on it, okay, all the time. We like to put subscripts on our delta H. And that's to indicate the specific enthalpy change that we are talking about. So for example, if we want to calculate or we want to describe the enthalpy change of a reaction, the delta H of a reaction, then we would put the subscript RXN for reaction. But we're also going to see that, you could have a delta H of anything. For example, let's say that I'm dissolving something. That would just be delta H. I might put DISS for delta H of dissolution, dissolving something, or I'm condensing something, delta H of COND, condensation. So that's the idea. The subscript is what's going to tell you the reaction or the process of this enthalpy change that we're calculating or describing. So this is just another way to put it into a diagram, very similar to what we saw earlier in the presentation. But now it has the delta H's on the diagram. That's the difference here. Is that a delta H of vaporization, for example, is going to be an endothermic process. It's going to be a positive value. So and these are specific for the substance and the process. So if I'm going to take water, H2O, and if I'm going to boil it, right, change it from liquid to gas, then that requires 40.67 kilojoules per mole of energy just to do that phase change. Okay, and so we call that the enthalpy change of vaporization, or delta H of vaporization. Okay, let's say that I'm going to take liquid water and I'm going to freeze it into ice. So I could have just legitimately put delta H sub FREEZE or something instead of solid, but you get the idea. It's the enthalpy change for taking water and making ice, or going from liquid to solid. So that's going to be a negative number because that's an exothermic process. Those water molecules have to release energy into the surroundings in order to become solid ice molecules. So it's a negative number, and it has a value of 6.01 kilojoules per mole. So these are numbers. These are essentially table values, right? You could look these up in a table for the different substances to use in calculations. You don't need to memorize them. They will be given to you. But what we do need to learn is how to use them in calculations, okay? And so we're going to use them in calculations with something called a heating curve. And so this type of graph is just tracking how the temperature changes as we change the amount of heat. Okay, so first of all, everything begins, at the lowest temperature, at the least amount of kinetic energy, so the least amount of, heat in the system as a solid. And so as I'm adding heat, I'm just warming up that solid. That solid goes from a lower temperature to a higher temperature. Okay, and that's all, that whole range, it's in the solid phase. Well, eventually what I'm going to do is I'm going to reach the melting point. I'm going to reach the melting temperature of that solid. Okay, so again, something I already said. So as the heat gets put in, so as we increase the heat of the system, it's going to result in an increase in temperature. Okay, so once I reach that melting point, that point at which it begins to change from solid to liquid, I'm going to go through this time period, or this phase, where we have a mixture of solid and liquid. So notice that throughout this whole time right here, I'm still adding heat, more heat, more heat, more heat, more heat, more heat. But my temperature is not changing. The temperature is flatlined. The temperature is not changing. And that's because all of that energy that I'm adding in this area, all that energy that I'm adding is going in to unlocking the solid molecules out of their position so that they can move around and become liquid molecules, still close together, attracted to one another, but free to flow around. So that's kind of the difference between solid and liquid, and that requires some energy. If I'm going to break them out of their positions and let them flow around, then I have to put energy into that system so that those molecules have enough energy to have that motion. Okay, so this is the second phase. So in this case, we have, like I said, it's the melting point, and any increase in heat, and that's what's going on as I'm progressing to the right here, all that heat that I'm putting in is going into the phase change, and that's why the temperature is not increasing, because that energy that I'm putting in is just doing the work of changing the solid molecules into liquid molecules. Okay, so now once everything has melted into a liquid, all the solid is converted into a liquid, that's when I can start warming it up again. And so now this line, this slope here, represents the liquid phase, okay? So once again, all the heat that I'm adding in this area is going into warming up those liquid molecules, giving them more kinetic energy, they're moving around faster. Average kinetic energy is connected to the temperature, so the temperature goes up. But once again, I can say an increase in Q is going to result in an increase in temperature. Okay, well, as we know, eventually that liquid is going to get to its boiling point, and so that's what this line represents. Okay, so it's right at the boiling point. And so the idea here is the same as what it was when we melted the solid. But that energy that I'm putting in, that increase in Q, is going into the phase change. And so that's converting liquid molecules into gaseous molecules. That requires energy. So it's not going to change the temperature, but it is very important because it's making all of those liquid molecules into gas molecules. And so once again, once I finally get to the point where all those liquid molecules have converted into gaseous molecules, vapor, then I have the gaseous phase or the vapor phase. And so I can start warming that up again. I don't know if you realize that, but you can, when you get to the gaseous phase, you really can continue to heat it up. That's why steam is often so dangerous, because it's not, it can reach temperatures much, much higher than just boiling water. It's the steam that can reach those super duper high temperatures. So again, any heat that I put into the system goes into increasing the temperature, okay? All right, so this is what we call a heating curve. Has a lot of just important information in it, okay? All right, so as I said before, you can also go in the opposite direction if the system is just releasing energy. So you could think of it in terms of, if I start with a gas and I cool it down into a solid, so it's going to lose heat and it's going to decrease in temperature, and then it's going to lose heat, but it's not going to decrease in temperature. It's just going to change from gas to liquid. And then once it all becomes a liquid, it's going to lose heat, and therefore the temperature is going to go down as a liquid. But then when it reaches the freezing point, it's going to I still can have it lose heat, but it's not going to change the temperature, because all that energy that I'm losing goes into converting the liquid molecules into solid molecules. And then once again, I get it to the solid phase, and if I keep cooling it off, I keep removing heat, then I can just cool off the solid until ultimately I reach absolute zero Kelvin. Okay, so here's just the picture for water. Here's the heating curve example for water. It's not in your notes. I just wanted to show you an actual one, okay, with the way that the slopes are and the size of the flat areas. Okay, notice that for water, the amount of energy that's required, so the difference between E and D, the amount of heat that you have to put in for boiling or vaporizing water is a lot bigger than what it is for melting ice. Okay. Those delta H values that you saw, for example, on the water chart, or that we defined earlier, we're going to use those in calculations. So that's what this part of the presentation is all about. So these have special names. So the enthalpy change for the process of melting something, or fusion, right? We call that the molar heat of fusion.
How you doing?
Okay, and to define it, it's just the energy required to convert 1 mole of a solid at its melting point to the liquid state. Okay, the energy required to convert 1 mole of a solid at its melting point to the liquid state. All right. And so if I want to calculate the amount of heat that is done, then one thing I need to know is the number of moles. Okay, because Q, the amount of heat in joules, is going to be equal to the number of moles of the substance times this table value, something that somebody grabbed from a table in a book somewhere, this delta H of fusion. Okay, something you won't have to memorize, something you'll be given. Okay, very similarly, you have this molar heat of vaporization. So it's just defined as the energy required to convert 1 mole of a liquid at its boiling point to the vapor state. And it has the same equation. So the amount of heat is just the number of moles times the delta H of vaporization. All right, now also keep in mind that you can have negative Q's and negative Q here and a negative Q here if this delta H is a negative value, because instead of melting, we are condensing the liquid to a solid. That would just mean have the same number for the delta H, but a negative sign. And if it's the same thing down here, if I'm taking a gas and I'm condensing it into a liquid, then it's going to be the delta H of vaporization, but with a negative sign. And so that would result in a negative Q. And that makes sense, again, because negative values mean exothermic process, and cooling things off and freezing, condensing them or freezing them. Those are processes that are exothermic because the energy goes from the system into the surroundings. Okay, so again, the signs are important. The signs on the numbers are important. They have meaning. Okay, so here's an example problem that we'll do. So calculate the amount of energy required to convert 237 grams of solid ice at 0 degrees to hot water at 80 degrees. And so we're going to need some of these, important constants from tables to do this calculation. For example, we'll need the delta H of fusion, which is 6.01, and we'll need the specific heat for water, 4.184. Okay, now what I recommend whenever you do these problems is to start off with a diagram that just it's like a heating curve. It won't be the full heating curve, but you can just draw out part of it that's applicable to the problem that you're given. Okay, I think I'll actually just do that with a pen here. So, we're going to plot the temperature versus the amount of heat that's being added, okay, because that's what we're doing here. We're adding heat to convert ice into water. So we're going to start at 0. So I know that that's an important temperature. We're going to start at 0, and then we're going to go up to 80. So that's another point that I'll put on my diagram. And so what we're going to do is we're going to start with ice at 0. So I'm going to add heat, and it's going to be flat because I'm not going to increase the temperature as I'm converting those solid H2O molecules into liquid H2O molecules. But then I'll get to a point eventually, I'll add enough heat to where I've converted all of those solid ice molecules into liquid water molecules. And then I'll start warming it up, okay? And then ultimately I'll get to that point where I'm at 80 degrees, okay? So that's the really crappy drawing. So what I'm gonna do is erase that, and I'll bring it up on the screen, and then I'll go back to the pen to do the calculation part. Okay, so Shift E. Okay, so yeah, plotting the temperature versus the heat. We know 0 degrees is an important point. And so as we melt the ice, we're going to label that as the first amount of heat, Q sub 1, right? And then once we get all that ice melted into a liquid, we're going to warm up that liquid to the other important temperature in this problem, 80 degrees, okay? And I label that as Q2 because, and you'll see why, because I'm going to calculate each of these Qs differently. I'm going to calculate Q1 in a different way than I calculate Q2, okay? So I think this is in your notes here. So here's kind of what I have to do. I have a mass, but I need to convert that into moles because this delta H value has units of moles in it, right? And I'm going to want that to cancel. So one of the things I'm going to need to do is convert this 237 grams of water into moles of water. So that's kind of step 1. Convert mass of the water into moles of water. And then I'm going to need to calculate the energy of just converting that ice into a liquid. And I'm going to do that with an equation for Q1. But then you'll see that I'm going to heat that water from 0, the liquid water, right? It's still going to be at 0 degrees, but now it's going to be in the liquid phase. And I got to heat it up to 80 degrees. And so I'm going to use a different equation for that. That's going to be Q2, okay? But for this second bullet here, for calculating that Q1, all I need to know is the number of moles, which I just did, and multiply that times the delta H of fusion, which I'm given, okay? And then for Q2, what I'm going to do is go back to what I learned yesterday, MC delta T, because I know the mass, 237, I know the specific heat, 4.184, and I know the delta T. Final temperature is 80, initial temperature is 0. Okay, so that's kind of the approach we're going to take with this problem. Okay, well, apparently I've already got some of it in there, but we'll have to just I'll talk around it and then we'll get to it. Okay, so like I said, the first thing I want to do is convert mass to moles. So I'm going to do that up here. So 237 grams of H2O, okay, and I know that 1 mole of H2O is 18, and I'll say 0.0 grams of H2O. Okay, so grams over grams cancel. I'll do that calculation real quick, so I've got a number to work with. Okay, so 237 divided by 18 is 13.2 moles of H2O. So 13.2 0.2 mole of H2O. Okay, so like I said, the first thing I'm going to do to calculate Q1, it's the number of moles times the delta H of fusion. Okay, well, I just learned the number of moles. It's 13.2. Okay, and the delta H of fusion is given to me, there it is, okay, times 6.01 kilojoules per mole. Okay, so moles cancel. And I'll let PowerPoint actually generate the number here, but it will have units of kilojoules. Okay, so that's Q1. Now Q2, like I said, is calculated with a different equation, and that was the MC delta T. Well, the mass I know, 237 grams. The specific heat I'm given, 4.184 joules per gram per degree Celsius. And then the delta T, the final temperature is 80, and the initial temperature was 0. Okay, and so that's going to result in some answer. Now, here's an important point. Because this has units of joules in it, what I generate is going to be in joules. And so I'm going to, and I think I mentioned this yesterday, you're going to have to reconcile those two. You can either, typically typically these will be expressed in units of kilojoules. So what I would recommend is just go ahead and convert this number of joules into kilojoules, but you could just convert the kilojoules into joules. The idea is that they have to be the same. Okay? All right, so now that I've done that, I will erase all that and we'll go through it in the PowerPoint. Okay, so calculating the number of moles, 13.2, and Q1, we just multiply 13.2 times 6.01, which is 79.3 kilojoules. And then Q2, as you can see right here, is the MC delta T. And so, oops, wait a minute. Oh, maybe I didn't finish that one. Let's see. Well, I guess I'll assign that to you. Now you know what to do. You're just going to add all of them together. So you got the Q1 and you got the Q2. So one thing you're going to need to do that I apologize, it's not on the PowerPoint, but you just need to add. So the total amount of energy Q, the total, it's just going to be Q1 plus Q2. Okay, and I'll let you finish that later. I'll put that in the notes before I upload the PowerPoint, but just so you know, that's how you finish it up. All right, so now that one's in the books. Now we want to talk about these enthalpy change values. We can manipulate them, and we want to talk about the rules we have for manipulating them. So let's say that we have this reaction right here. We have nitrogen plus oxygen, you give 2 nitrogen monoxide. The delta H of that reaction is positive 180 kilojoules. Let's manipulate this reaction. First thing you want to do is reverse it. So what if I just had to reverse the reaction? So in that case, 2 nitrogen monoxides break apart and form a nitrogen and an oxygen. So you should know what we need to do to the delta H to represent that idea, that concept of reversing the reaction.
What is this, bizarro world?
So if I just took these products and created these compounds, or pardon me, these elements, right? The pure element nitrogen, pure element oxygen, that would just be the negatives. That's the key. It's just the negative of the delta H, what it was originally. So if I manipulate the reaction by reversing it, I manipulate the delta H by making it negative.
That's messed up.
Okay. Well, what if sometimes you might need to multiply the whole reaction by some factor, like multiply the whole thing by 3, for example.
Wow.
So that would result in 3 nitrogen plus 3 oxygen to give 6 nitrogen monoxide. And you just do the same thing to the delta H value. So if I multiply the reaction by 3, then I multiply the delta H value by 3. If I multiplied it by 2, then I multiply delta H by 2. If I multiplied this reaction by 16.721, then I do the same thing to the delta H value. Okay. So those are the 2 rules we need to understand from manipulating reactions and how it affects the delta H value. So that's kind of some precursor information to our next topic. Okay, so the next topic we need to go over is something called Hess's law. And I have this analogy that I usually use for Hess's law. So let me talk about that. So, here we are in Joplin, right there, right? Now, we're a small city, so we have an airport, but it only goes to, it goes to Dallas. If you want to take a flight from Joplin, you have to go to Dallas, or now you can go to Chicago. Okay? Well, I can't go, let's say that you wanted to defect from the United States of America and you wanted to go live in the new nation of Chaz, right? So you can't, there's no way you can take a direct flight from Joplin to Seattle, let's say. Okay, that's not possible. Okay, I was born in Seattle, by the way. But you could get there. You could defect there if you wanted to, but you would have to do it indirectly. You'd have to fly to Dallas and then to Seattle, or you'd have to fly from Joplin to Chicago and to Seattle. Okay, so it is impossible for us to go directly from Joplin to Seattle, but you can do it in steps. You can go to Chicago and then to Seattle, or the same thing with Dallas. And so what you're going to see is that some chemical reactions are exactly like that. I won't be able to figure out the enthalpy change of the reaction directly, but I can find out indirectly. I can learn it indirectly if I can determine the delta H of reactions that ultimately add up to the same reaction. Okay, that's one analogy of Hess's law. All right, so let me go back to the presentation here. So Hess's law, is defined like this. So the total enthalpy change for the reaction is just the sum of all the enthalpy changes involved. So let's say that I have this reaction, methane plus water to give carbon monoxide and 3 hydrogens. That has a certain enthalpy change associated with it. And let's say that I know what that is. And then there's another reaction, carbon monoxide plus 3 hydrogens. So notice that those are the products of this first reaction, plus another water molecule. And that becomes 4 hydrogen and a carbon dioxide. And let's say that I know the delta H of that reaction. Well, if I just combine these 2 reactions, you see that I've got carbon monoxide on the left and right, and 3 hydrogens on the left and right. So they cancel. And so the overall, if I were to add up these 2 reactions, I would get this overall reaction right here that has an enthalpy change. Okay, so Hess's law is just saying that the enthalpy change of this reaction, that is the sum of these 2 reactions, is just the sum of these 2 delta H's, okay? Delta H3 is just the sum of delta H1 and delta H2. And so the reason why this is important is because for whatever reason, I might not be able to get the delta H of reaction 3 directly. But if I can get the delta H of reaction 1 and reaction 2 directly, then I can get the delta H of reaction 3 indirectly simply by adding the other 2 together. Okay, so that's the concept behind Hess's law. But what you're going to see is you may have to manipulate these reactions that are components of this sort of target reaction. I may have to manipulate these. I may have to reverse them or multiply them by a factor, like you just did in the previous slide. Okay, so this is just kind of an example that you know, it's just in pictures what you saw in the previous slide. This is also in your handout there. So the idea being that, you know, I can't really monitor this right here. The methane plus 2 waters becoming these products, 4 hydrogens and a carbon dioxide, that, you know, let's say for whatever reason I cannot measure the enthalpy change directly for that reaction, but I can monitor the enthalpy change of this first reaction.
Kind of makes you cry, doesn't it?
So for some reactions, you know, it's impractical to determine the energy changes directly, and I even comment why. So usually it's a kinetics thing. It usually would just take too long. So a lot of times the thermochemistry is determined indirectly. So, you know, knowing this delta H and knowing this delta H, we just combine them together to get the delta H of the desired target reaction. All right. Okay, so let me do another example here. So using the following data, calculate the delta H of the reaction for this reaction right here. So this is our target. I need to manipulate these 3 reactions in some way so that they add up to make this reaction right here. And so this is the strategy that I usually employ. And so some of this is just kind of hints and tips. But what I do is I look at the target, and I look for things that I want in the target, and I look here with my sort of my set of building blocks, and I see if I have any of those compounds in the right place and in the right amount. So for example, I want C2H4 on the left side. So, okay, so here's one that's got C2H4 on the left side, and it's in 1 mole. So 1 and 1. So I'm going to leave this reaction alone. Right now, I'm just going to, you know, leave that one alone. Okay? Now, what about H2? Well, I've got some other options there. So this one has H2 in it, okay? And it's on the correct side, and it's in the correct amount. It's got a 1, it's on the left, it's on the left. So I'm going to use this one exactly the way it is. Okay, well, what about this one, C2H6? Well, here's a reaction with C2H6 on it, but it's on the wrong side. Okay, I need it on the product side. Right now, it's on the reactant side. So what I'm thinking about doing is just reversing that reaction right there, which is going to make that a positive, right? And so then after you do that, just go ahead and add everything together, and usually things will cancel out correctly, properly. But if it doesn't, then you might think about using some coefficients to get it to cancel out correctly. Okay, so let me erase that, go back to, oops. All right, so we have the delta H values for 3 reactions, and we need to combine them in such a way that we can obtain the reaction, this target reaction. That's the goal. Okay, so as I said, we will need to reverse that 3rd reaction to get the desired product on the right side. In this case, you know, right has dual meaning, correct and physically the right side. Okay, so we're going to, you know, just reverse that reaction. So what were the products are going to become reactants. Oops, and the 7 halves didn't move over quite well. I'll have to change that. But again, you see this 7 halves right here? That should be, you know, nudged over next to the oxygen. And so that means I just need to change the sign on the delta H value. Okay, so that becomes a positive 1560. And then you just see if everything cancels out the way that you want it to. So I have 2 carbon, you know, if I added all this stuff together, 2 carbon dioxides, they cancel out. I have 3 waters on the left, and on the right, I have 1 water and 2 waters. So 3 waters on the right, so they cancel out. And so if you look at the oxygen, 7 halves is the same as 3 1/2, right? So that means all my oxygen cancels as well. So everything cancels that I want to cancel, and what I'm left with is all the good stuff, all right? So I did it correctly. I manipulated these 3 reactions correctly in order to get the target, the goal reaction. So once I'm convinced that I did that correctly, all you need to do is just add these 3 numbers, manipulated or not, together. Add all those delta H, the reaction values together, you get a negative 136.8 kilojoules. Okay? All right, so that's an example of Hess's law. I think I have, oh wait, so I'm just gonna do another example, and then I'll give you guys one to work on. So once again, 2 reactions here. I have iodine fluoride plus fluorine to give iodine trifluoride. And the second reaction, iodine fluoride plus 2 fluorides to give iodine pentafluoride, right? And each of those has a delta H associated with it. And so I'm going to use those 2 components to manipulate and come up with this reaction right here. So how can I manipulate these 2 reactions to get this reaction? And so once I do that, I do the same manipulations to my delta H values, and then I add them together to get the delta H of this target reaction. Okay, well, once again, the strategy that I employ is to just look for what I need, where I need it in the correct amount. So what I need is I need IF5 on the left. Well, here I've got IF5, but it's on the product side. So what I need to do, I'm thinking I need to do is to reverse this reaction right here, okay, which is going to make that a positive, okay? And I need IF3 on the product side. Well, here I have IF3 on the product side, 1 mole, 1 mole. So I'm just going to leave this one alone. I'm not going to do anything to this one, okay? And I need F2 on the product side. I need some F2 on the product side, 1 mole of it. Well, okay, so when remember, I already decided that I have to reverse this. Well, if I reverse this, then it's going to put 2 moles of F2 on the product side. And I see up here that I've got some F2, so it might cancel out the way I need it to. So for now, I'm going to be happy with my decision. I'm just going to reverse this one. I'm going to add the 2 together. So I hope you get the sense that, you know, there's going to be a little trial and error with these, and that's okay. All right. Okay, so, oops. Okay, so we need IF5 on the left, so it's reverse reaction 2. So IF5 reacts to form IF plus 2 F2s, and so that gives me a positive 745. And so then we just, you know, decide that we're going to add the 2 reactions together in that way. And so we've got the reverse reaction that I just did, which is this one down here at the bottom. And I've got the first reaction, reaction 1, the way it's given. Okay, so if I add things together, okay, I've got IF on the left, IF on the right, so they cancel out. And then this is nice because I still want to have a fluorine on the product side, and I've got 2 of them, but and I've got 1 fluorine on the reactant side, so that will cancel. So that one cancels completely, and I get rid of 1 of the fluorines on the product side. And so everything that's left over
too easy.
is just the sum. Okay? And the sum is the reaction that I'm shooting for. That's my target. Okay, so since those agree, since all that agrees, then all I need to do is just add together these manipulated numbers. So basically it's 745 minus 390, which comes out to be 355. The standard enthalpy of formation, and the standard is symbolized with that superscript degree sign. That's what that means. So it's the enthalpy change of the process of forming 1 mole of a substance at its standard state from its constituent elements in their standard states. And we just define standard state as the most stable form when you're at 1 bar of pressure. Remember that 1 bar is the same as 1 atmosphere effectively, and 25 degrees Celsius or 298 K. And so it's indicated by that superscript degree sign. That's what that means. It means the standard conditions. Because you can understand that anytime you're going to make a table of values, all of those values have to have been obtained under the same conditions. So it's a set of standardized conditions. So that's what that means. All right, so for example.
That's high quality H2O.
So, you know, the delta H of formation of water, for forming water, we start with the constituent elements. Water has hydrogen in it and oxygen in it. So if I start with those 2 constituent elements and I make water, the enthalpy change of that reaction is what we would also call, or could also call, the delta H of formation of water. And so you just look that up in a table. Okay? All right, now, how do we use those to determine the delta H of a reaction? Well, it's a simple equation that is on your equation sheet. You just need to learn how to use it. Okay, and we can just use all these table values of delta H's of formation, which we have a very, you know, condensed or subset of the table in your handout there. And that equation. So I know the Twilight music, or the Twilight Zone music, because it looks weird, right? It's got a lot of pieces and parts to it, but really is a pretty simple equation. Okay, so if we're going to calculate the delta H of a reaction, I just need to look up all the delta H's of formation of the products in a table, and I need to add those together. That's what this symbol means, the summation. So I add all of those together, but I also have to multiply each of them by the balancing coefficient. And then I'm going to subtract from that the same thing for the reactants. So I look up all the delta H's of formation of the reactants, and I add those together, multiplying by their balancing coefficient. And so I subtract that total from the total for the product. So it's products minus reactants, products minus reactants. So drill that into your brain. But again, this equation is on your equation sheet. You just need to know when to use it and how to use it. And so this little note is important, that if it's a pure element, then the delta H of formation is 0. And that should make sense, because the way we defined it, we said that the delta H of formation is that energy change, that enthalpy change, when I go from the pure element to the product. Well, if the product is also just the pure element, then there's no change, so there's no energy change. Okay, so a little example here. So we're going to use the delta H of formation values for substances in table 5.2 to calculate the delta H of the reaction for this reaction right here. Okay, N2 plus 4 NH3s to give 3 N2H4s. Okay, so once again, I'm going to go ahead and show this equation, because this is going to be given to you. Okay, so we're going to utilize this equation that's given to you on your equation sheet. And so the first thing I need to do is to look up the delta H's of formation for all these products. Well, there's just one product. Okay, so the delta H of formation of that product, you go down here and you look up that, and it's a gas. Now, that's one thing to notice with these tables, is that many times here we go. So many times you're given the substance with 2 different phases, and you have to use the correct one. So in this case, I want to use the one for the gas, which is 95.4. So this is 95.4. Okay, and just for the sake of saving space, I'm not going to write the units, but remember the units are important. And this multiplier is going to be a 3. Okay, so I'm going to subtract from that the delta H of formation of each reactant. And so for the N2, I know that that's going to equal 0, because that's just a pure element, right? And then for the NH3, I'm going to multiply by 4 because of this 4. And then I just look up the value for NH3 gas, which is negative 46.1. So negative 46.1. Okay, so then you just do all the math, and that's going to be some number of kilojoules, okay, per mole. And that's the answer to the question. Okay, so I'll erase that, and I'll show you the solution in PowerPoint. So again, we just substitute in the individual terms, look up the numbers in the table. Nitrogen 0. All these multipliers come from the balancing coefficients, and I just have to remember to look up the right phase. Like I chose gas instead of liquid for the N2H4, because that's the way it is in the reaction. You do the math, and you get 470.6 kilojoules per mole. So again, you're going to use this equation, the delta H of the reaction equation, when you're given the delta H's of formation. Okay, so that's kind of the indicator. If you're going to, if you're ever wondering when you're going to use this equation, well, if you're given like a table with these delta H's of formation in it, that's a good indication that you're going to use this equation to solve the problem. So the answer you should have gotten is negative 890.3 kilojoules. Okay, hopefully, or something close to that. Sometimes the table values are different from table to table, so don't worry about that too much.